Hello everyone, this is Ashwin here. In this video, we are going to learn about complete Pytorch tutorial. So I'm going to do Cassava leaf disease classification project. On the way, we are going to touch all the parts of Pytorch. So we'll be learning the complete end-to-end Pytorch tutorial in this project. So it will be very helpful for reusing the same snippet of codes for other projects also. So we will be touching the basics like how to load the data from the disk using Dataloaders, and how to augment the data, and how to create the models, and how to train using Pytorch, and do all the stuffs in this project. So what is the difference between Pytorch and TensorFlow? TensorFlow usually have some reasonable number of parameters that we can fine tune, but it have some limitations. But in Pytorch, we can do as many customizations as possible, and it is also easy to debug. And it also has many advantages. You can refer the documentation to see clearly about that. Now let's dive into the project. So for this project, I'm going to use this competition. So I already attended this contest, and I have built the code using Pytorch, and I have got around 86% or around 87, I guess. But to get that accuracy itself, it took like a longer time to train, and also I have to do so many advanced techniques in order to reach there. So in this video, we will see the baseline code on how to proceed with all the data. First, we have like train images and test images. We have like 15,000 test images. So currently we just need the train image, and the dataset size is around 6 GB. So that's a lot. Maybe if you discard these test TF records or this train TF records, maybe it will be less. So this is the train images and test images. Currently we have one, but while submission it will have the full images. And this is the label num2 disease. Like, it's kind of a label encoder. We can use this number to identify what is the exact disease. So these are all 4 different types of disease in the leaf, and the last one is healthy. So we have train CSV that we can see it in the code. Maybe let's dive into the code so we can see everything more clearly. So this is the Kaggle notebook. I didn't enable the GPU yet. We will enable it later. So first we will import the modules. So we will definitely gonna import a lot of modules here. So import modules. So first we will import the basic modules, and after that we will import additional modules. Import pandas as PD, import numpy as np, import time, import OS to deal with the files, import copy to copy some weights of the model. We will use this later. And import Seaborn as SNS. Just leave a space for visualization. Import matplotlib.pyplot as plot, and from pill import image to load the image and display it. And also we have to import JSON. Import JSON. This is for the class file we have seen, that is 0 to that particular class file. Key will be the number, and value will be the class name. So like that we have to process. We will see that later. Now apart from that, we have to import few modules for Pytorch. So import torch. I'll also comment it. Visualization module, and this is Pytorch modules. Okay, now here we have to import more, that is import torch.nn, that is neural network as nn, import torch dot optim as optim, from torch.nn import functional as f. So this is for getting the activation functions. Each module have separate functions. So this is for optimizer, and from torch dot utils dot data import dataset comma dataloader and yeah, I think that is enough for now. From torch vision import models. So using this we will be importing some models like ResNet 50 or 152. You can import all the modules with weights, and you can use that model for this project. It's also called transfer learning, so we'll be learning about that too. And lastly, import torch vision dot transforms as transforms. Okay, this is Pytorch modules, and apart from that we have to import for augmentation. So for that, import augmentations. It's not suggesting. I hope this works. From augmentations dot pytorch dot transforms import to tensor version 2. Why this is added? Okay, now this will be to tensor v2. So we'll be using all these modules. I know this is a lot. We usually like import these modules, like 5 to 6 modules hardly for all the basic projects. So this is just gonna be a longer one because we are going to explore all the parts for Pytorch. So let's run this. Okay, I'm facing some error here. So here I made a mistake. This is transforms. Run this. Now all the modules have been imported. So that is the first step for us. We have to still do a lot of steps. Now we have to load the training data, and also we have to load the JSON for the mappings. So let's load the dataset. So now we have to define a directory. So base underscore directory. So I'm just mentioning some variables in capital letters, means we won't be changing that variables. This is just for like configuration or using that variables. That's why. So now we have to set the base directory, that is the path to the dataset. So this is the dataset we are having. I'm going to set this path so we can get the train CSV and all the images. So that will be /input/ Cassava leaf disease classification. So this is the base directory. Now after that, train equals pd dot read CSV base directory. Okay, it's not suggesting. Base directory plus train dot CSV and train dot head, and this. Okay, now we have loaded the dataset. So this is the image ID and the corresponding label. So we will delete this. Maybe for the configuration we will just have it in a separate cell. Okay, that's done. Next, we will load the mapping. So with open, again base directory plus label. Okay, this will be label num disease. Okay, it's not suggesting. I'll just copy file path, paste this. Okay, just giving the whole thing. I'll just use this JSON. Okay, as f. Now this is a JSON file. So mapping equals JSON dot loads of f dot read. So f dot read will read the whole file, and using JSON dot loads we are loading the JSON, and after that we will be converting into like a dictionary. So mapping equals, so int of k colon value for k comma v in mapping dot items. So we have converted this into a dictionary and we will print it. So mapping, so this is the dictionary we are having. So for the 0th key, Cassava bacterial blight, so this is the label string. So we can replace it, or we can use this for our inference purpose. So this is the mapping variable we are having. So that's done. So loading mapping for target label. Okay, now that's done. Now we will create a new column for the train data. So here for the corresponding label we will be having the string. So for that, train of label underscore names equals train of label dot map of mapping. So what it will do is it will get that labels here 0, and using the mapping it will get this string. So like this it will do for all the rows, and it will create a new column. So now let's display the head of train. Now see, you can clearly see for 0 CBB, and for 3 that is CMD. So for all the labels in integers we got the string representation, so it will be easier for inference. Now we have done loading the data set, and we have explored a little about what is the data. Now we have to go for exploratory data analysis. So exploratory data analysis. So now for this we have to define a function. So here I will be defining a function called plot images, so we can able to easily plot the images for all the corresponding classes. So it will give us a better idea of seeing different images for each class. So def plot images of class ID. So for the corresponding ID we will be getting the images. Label we will pass, and total images. If nothing is passed means by default we will be setting it by 6. So that's it. Now we will do the coding. Now we have to get some image IDs for the corresponding class ID. This is like a filtering process. Get image IDs corresponding to the target class ID. So here I will have plot list equals train of okay, train of label. So based on the label we are going to filter out. So equals class ID that we will be specifying. So now after filtering we have to sample total images. So total images, and from this we have to get only the image IDs. So that will be image underscore ID dot to list, and I am converting that into a list. So first we are filtering out the whole data frame for the corresponding class ID, and after that we are just randomly picking the total number of images. Currently it is 6, and after that we are getting only the image ID column and converting that into a list. So this plot list will contain 6 image IDs like this JPGs. Now after getting the plot list we have to get the labels, like for plotting purpose. So for that, labels equals label for I in range of total images. So it's just a repetition of labels. So if you pass healthy means it will have healthy 6 times. That is the total number of images. Now after that we have to define the size. So if you are just changing the number means this snippet will help you. So size equals np dot sqrt of total images. So we will convert this size into a integer. Now if size multiplies size less than total images, then size plus equals 1. So this is dynamically allocate our subplot size. Now we have to set the figure size. Set figure size, and this is dynamically set size for subplot. Now for the figure size we can have plot.figure fig size. I will have 20, 20. Now after that plot the images in subplot. So here we will loop over the images for index comma image ID comma label in enumerate of zip of plot list comma labels. So inside the loop we will set the subplot first, plot dot subplot of the size comma index plus 1. So enumerate usually will start at 0, so that's why the index will start at 0. So if you pass 0 means it will show an error. That's why I am adding a plus 1 to it. And after this we have to load the image. So image equals image dot open of, we will pass the image ID. Okay, before passing we have to set the directory. So string of, so this is base directory plus train underscore images slash plus image underscore ID. So here this is the base directory, and here we have the train images, and after that this is the image ID. So that's how the path works. Now after this we will go for plot dot imshow image and plot dot title, that will be label, font size equals 14. Finally plot dot axis off, or else it will show some axis that is not needed. Finally plot dot show. So this is the function. Let's see whether it is working or not, or else we have to do something else. So first we will go with the first class. So plot images of class ID. So class ID will be 0. For that particular class, I can have mapping of 0. So this will pass the class name. And after that, we have to set the image number. I will have 6 alone. And that's it. Let's plot. Hope this works without any errors. Let's see. Okay, it is working fine. So we are having a bigger plots. Maybe we will adjust this 15, 15. So run this again, because those are all like bigger images. Now this is clear. So here this is CBB, Cassava bacterial blight. We can see several different types of disease. So here everything is like yellow color, and here we have seen some holes, and this image seems like a healthy one. I don't know whether it is considering the whole image or this particular leaf. So that may come into like a misclassification. So similarly we will do it for all the remaining classes. So this will be 1, 1. So defining functions will make our process easier and the code will be much neat. And here this is Cassava brown stick disease. Okay. Here I can see some brown, and here I can see some brown color on the leaves. And these all seems like healthy. Maybe we will run it again to get a different sample. So sample means it will randomly select some images for that particular class. So be sure to remember that. So now this is a different set of images, and here also I can see some yellow leaves and brown stick disease. I think we have to get some domain knowledge for these diseases, like how we can classify this. I don't know whether it is the stem or the leaf. I think it's the leaf, and maybe some of them having the diseases. We have to look into this particular label further. It's not much clear for us now. Let's go for the next class, that is 2. So Cassava green mottle. So you can clearly see the spots like in the leaf. It's having like multiple yellow spots in the leaf for all the images. So this disease is somewhat clear than the other. Let's go for the last one. I think we have copied. So that is 3. So this is the disease types. And lastly, we will see about healthy ones. Cassava mosaic disease, and here I can see a little bit of yellowish at the center of the leaves, and all the leaves having the same pattern. Let's rerun it again to check whether our assumption is correct or not. And yes, it's also having yellow spots, but kind of different compared to other. It's like having more yellow spots, but here it's kind of having a different pattern or texture. Now the last one, 4, that is the healthy ones. Okay, this is 4. Sorry for that. Let's rerun it. Okay, now this is the healthy ones. So here the healthy ones are like the leaves are much clear, but this leaf is like definitely damaged. So, and here also some leaves are having a yellow color. So these kind of images may cause some misclassification. So while using some advanced techniques, we may have to like remove some of the uncertain data. So here if I want to remove some picture, means I can remove this picture as healthy, so we can like ignore it. So the model will better understand what is meant by healthy leaves. So that kind of technique we have to do if we are competing in some kaggle contest or any other hackathons. So that is one of the methods. So these are like exploration of the disease on the particular leaves. We can also do some more exploratory by clustering some images and doing some feature extraction, all the things we can do, but we are focusing on the Pytorch here. So I'll go for the last thing, that is the label distribution, like how many samples are there for each class distribution. So here SNS dot count plot of train of label names, run this. So this is the count plot, one class having a higher number of samples. Let's rotate the class names. So plot dot xticks of rotation equals 90, run this. Okay, it's also displaying other things, the array, and we are also getting some warnings. I think I forgot to import the warnings class. So at the end we will import warnings and warnings dot filter warnings. I will ignore all of them, and also we can have matplotlib inline. So let's run this. Okay, it's importing the modules. It didn't show any error. We can proceed further. So here I will rerun it again. So I didn't face any warnings here, but the text are there. Okay, we will leave it. So here Cassava mosaic disease having a high number of classes, that is around 13,000, and the other classes having 1,500 here, or 1,000, 2,000, 2,000 and 2,500. So that is the number of classes we are having. So we can proceed in two ways now. We can proceed as it is. So if you face this imbalanced distribution, means you definitely have to reduce the number of images for this class. You can randomly undersample the image, or else you can uniformly distribute the classes, like you can oversample these classes and undersample this class, and you can have a total of 4,000 images for each class. So you can use some smart or weighted random sampler, like that. You can use any techniques you want. Currently I'm just gonna proceed further, and in Pytorch cases we'll be defining some function called sampler or weighted random sampler to reorganize this uniform distribution to load the data, but I'll cover that in a separate video. So these are for exploratory data analysis. We have explored pretty much all about our data set. Now we will do some configuration for our model and all the data loaders, and we also need to do a lot of custom data sets. Let us see. First, configuration and utility functions. Okay, now for the configuration I have to set multiple things. So first, the dimension equals, this is image width and height. I can specify a lower image size, but the classification result will be poor. So for this one I will set it as 256. After that, width, I'm gonna define everything in capital. This is like a configuration, that's why. Width and height equals the same dimension. After that, number of classes, num classes equals 5, and number of workers, num workers equals 24. Train batch size, okay, train underscore batch size equals 32. You can set higher batch size if you have a bigger GPU. So I'm gonna set a reasonable range, that is 32. Similarly, test batch size equals 32. Now seed equals 1. Device equals CUDA. So CUDA means we are going to utilize GPU for all the processing. We will be enabling the GPU after some time, so we will do that. And after that, so mean equals, so this is for augmentation purpose. I'm just specifying the mean and standard deviation. You can get these values in Pytorch documentation itself, or the augmentation documentation. So that will be 0.485, 0.456, 0.406. This is mean, and standard deviation, that will be 0.229, 0.224, and 0.225. So these are all the configurations. Let's run this. So now we have to set some augmentation. So for that we will be defining a function, augmentations. Now def get test transforms. So here val equals val. By default I am just setting it as a validation phase. So if I can say value, so it will be easier, value equals train. So if it is for the train data, what type of augmentation we have to do? So for that, return augmentations. Okay, why it's not suggesting? Augmentations dot compose of, you have to pass the list of augmentations here. First one, we will resize the image. Now augmentations, I don't know why the suggestion like takes so much time. The first one we will be resizing the image, that will be width and height we have set it. So width comma height. After that, again augmentations dot horizontal flip. So the retrieval will definitely take some time. So p equals 0.5, and after that augmentations dot rotate. The rotate limit will be equals minus 90 plus 90. After that we can also do vertical flip. It's definitely taking so much time for suggestions. So vertical flip, Again, this will be 0.5. Again, it's like messing up the code. And here P is like a probability. There is like 0.5 chance of probability it does a vertical flip at that time. So for the horizontal flip and the vertical flip, I'm just setting the probability as 0.5. So there's like a 50-50 chance it will do the flip, or it will just pass it as it is. The last we can do, I have to like type the full thing. See, suggestions is like messier. Normalize of, we have to pass the mean that we have set, standard deviation, max pixel value, that will be 255, that is in the range. So max pixel value is 255, that is in the floating. Lastly, always apply, always underscore apply equals true. Okay, that's done. So this is the augmentation we are going to do for training. I don't want to do so many augmentations for this. You can also do center crop or randomly crop the image. So this is just like a pipeline. So you can do anything you want. So this is for the training. Now for the value equals validation, that is val. So if it is for validation, means we just need to do the resizing and do the normalization. So I'll just copy this and paste it here. Just remove these intermediate steps, and that's it. It will just resize the image and normalize the data. That is just standard pre-processing you can do. So why we are using augmentations? If you don't use augmentations, means the model can't learn different view of images. So if you do horizontal flip or vertical flip or rotate the images, means it will have like a different views of the training image. So for testing, we don't need anything. That's why we are just ignoring this augmentations. So that's it for the augmentation. Let's run this. Okay, again this messed up. I don't know why it's happening for here. This is also like that. Run this again. Okay, now it's fine. Now we have to define a dataset class for this project. So this is just like a custom data loader. So dataset loader class. Okay, now here we will create a class Cassava dataset. So you can redefine this class for any dataset you want. Dataset. Now we have to define the constructor, that is init. So def underscore init, pass the self. Now we will be passing image IDs, labels, dimension equals none, and augmentation equals none. So if you don't pass the augmentation, if you didn't specify the dimension, it won't care. So it will just pass it as none. So these two are important. So that's why I'm just specifying it as the labels. And finally, we have to specify the folder. We have like two folders for training and testing. Folder equals train images. So that's done. So if you specify the folder, means it will just fetch the image from that particular folder. Now we have to initialize the super dot underscore init. This will just call the base class constructor, and after that we will initialize the variables for this class. So self dot image underscore IDs equals image IDs, self dot labels equals labels. So these are like parameters, and self dot dimension equals dimension. If we pass any, it will just specify the dimension. So self dot augmentations equals augmentations. Again, if we specify any, it will just assign, and the folder. So all the initialization has been done, and now we have to overwrite few functions. Now def underscore length. So if you call the length, means it will return the total length of the data set. So self return length of self dot image underscore IDs. Okay, so this will return the, so this will just return the total number of images. And after that, we have to override one more function, that is get item. Def get item. Now here we will be passing the object and the index. So for this particular index, it will try to fetch the image. So that is the purpose of this get item function. So I'll just also comment it. Returns the length. Okay, I'm facing some issues. Let's see. And here I'll be having return the image and label for that index. Okay. So currently I just restarted the session again. I think there is some issue in the kaggle. So in the meantime, we will just complete this code part. So now we have to load the image. So img equals image dot open os dot path dot join. So I can have base underscore directory comma self dot folder. So that is this folder, and after that I can have self dot image IDs of the index. So using this we can get the image, and after that we have to resize the image. So if self dot dimension, like if we have any dimension specified, means we have to resize. So I'll say img equals img dot resize of the dimension, and after that, if we specified any augmentation, self dot augmentation, then augmented equals self dot augmentations of image equals img, and after that image equals augmented of image. So this will just do the augmentation, and finally we will get the image. This can also have same img. Now finally label equals, we have to convert those labels into tensor values. So torch dot tensor of self dot labels of index comma d type equals torch dot long. So this is the data type we are just converting. So everything in this Pytorch will be everything, the input and output, everything will be converted into tensors. So with the help of tensors only, the GPU can do all the calculation. It can able to access all the values, and after getting the label, we will return image and the particular label. So this is the whole data set. Okay, so far we have completed the dataset loader. This is like a custom class. So here in the get item function, we are returning the image and the corresponding label. So label we are just converting into tensor value, and for the image, because of this augmentations, we'll be converting into a tensor later. So in this augmentations itself, we have to convert it into a tensor. So we have to add that line. So this will be 2 tensor v2 of probability, that will be 1. So for all the times it will be converting into a tensor values. So that is our ending output. So for validation set also we have to convert it into tensor values. So this is done. Let's run this once and it will be completed. Now after this we will create the data loaders. So create data loaders for training and validation. So this is like a image generator or generator. So if you have used Keras, means they would have a generator. So similar to that, we are going to have a data loader here. So let's create one. First we will initialize the class. So first we have to do it for training. So I will say train dataset equals Cassava dataset of, we have to pass the parameters. So we'll pass one by one. First we have image ID, image IDs equals. So here we have to pass the values. So before that we have to split the data for training and validation. We will split it here. I will also create a markdown so it will be easy. Train test split. So for this I'm going to import a module from sklearn.model selection, import train test split. I think most of the time it's not giving suggestions. Test split. Now here xtrain, xtest, ytrain, ytest equals train test split of train of image IDs, that is image underscore ID, and here train of label. This is the integer label we have in the data set, and after that test size equals 0.25. I am taking 0.25% of the whole data as a test data. Run this. So this will split the data for us, and here we will pass the training data. So xtrain dot values. So this will pass all the image IDs of the training data. Now after that labels equals ytrain dot values. So this will pass all the labels, and after that augmentations equals get test transforms of train. So we need augmentations for training. That's why I'm specifying this as a parameter. And after that we will specify the folder. For folder you can pass this train images as it is, but we don't need to pass because all the data we are going to get it from the train images only. So we can ignore this. We'll just have the dimension. So dimension equals, that is the dimension we have specified. So this is the custom class for the training data. So now we will specify the data loader for training. So I will call it as train loader equals data loader of, we have to specify the parameters. So first we will pass this custom data set. So train data set, and after that batch size. So batch size equals train batch size, we have already specified. Now number of workers, how many workers you want to work. So num workers equals, that also we have, so num workers. And lastly shuffle equals false. So we don't want to shuffle the train loader for now. And for the shuffle, so for this data set you can set it as true also, it won't cause any error. But if you are using some data set with the continuous values, means don't use the shuffle. And apart from these parameters, you have sampler, that is if you have to get the equal distribution of classes or get some specific image IDs from the class, means you can have your custom sampler. So I have specified those while doing the contest, but I'm going to go with this basic parameters. So this is for training. Let's run this once, and let's see whether we can get the train data set. So train data set of 0. So here I am facing an error, that is self.dimension. Again run this and this too. So now here I am facing another error, that is image should be an NumPy array. So here after loading and resizing the image, I can convert it into a NumPy array. So here I can have convert to NumPy array. So that will be img equals np dot array of img. So that should do it. Run this and run this again. So now you can clearly see it, right? So these are the image values in tensors, and this is the label. So these two things we are returning. So if you say 1, and again it will just get the second image ID, and like that you can change the index values. So we are just passing the index here, and it is fetching all the image and corresponding label here. So that's how it works. So I will delete this, and we will do this for the validation too. I'll just copy and paste it to reuse. So this will be val dataset, and in the val dataset we'll be using xtest for values and xtest.values, and here transforms will be doing it for validation. And after that this is done, then we will create validation loader. So we will pass the validation data set we have created here, and this will be train batch size itself, and everything remains the same. So that's it. Let's run this once. Okay, let's check it. So val data set of 0. Okay, here I'm facing some error. So this will be y test. Run this again. Now we got all the necessary values. I'll comment this to check whether data set is working or not. So this can fetch the data based on index. So dataset creation and data loader is done. So currently I'm just using a custom class for our project. You can also use some default dataset, that is this module we have loaded. So I'm just overwriting that module as a class here. So here you can see I'm just using this dataset as a base class, and that's how it works. Okay, now let's go to the next part. Now I'm going to create the model. So I will call it as, so create pre-trained. So we can call it as use pre-trained model, or it's called transfer learning. Now for this I'm going to define a function. So def get model. So here I'm going to create a network. So net equals models dot RESTnet. So here these are the types of RESTnet we are having. So initially I just used RESTnet 50, but it's like a small network. This big of a data set, it's not a sufficient network for us. So at the end I have gone for RESTnet 152. So that is like a larger network, and it has so many parameters too. And it took a lot of time for me for training. So initially if you want to play around means you can go for RESTnet 50. So and at the end you can go for RESTnet 152. So that is the biggest model, and it can give you a best validation accuracy. So I'll go for RESTnet 152, and I can load the weights later. So pre-trained equals true. So I'm going to use the pre-trained weights. So if you set it as false means it will just get the model architecture without any pre-trained weights. So after getting the baseline network, we can freeze all the layers. That is for param in net dot parameters param dot requires grad equals false. So it means I'm just freezing these layers. Freeze all the layers in the network. So why I am freezing layers means we are just going to train only the fully connected layers to do the classification. If you unfreeze the layers and train the whole network means it will have more number of parameters, and it will take more time for training. That's why I'm just freezing the network. I can also show you later how to unfreeze specific layers and train those layers alone. So it will be very helpful for fine-tuning the model. So currently I'm just freezing all the layers. If you want to train the whole network means ignore this step. So I'll also comment it. If you want to train the whole network, comment this code. Okay, that's done. And after that we will be getting some features. I will call it as num features. This is the end features we are getting from the network. So that will be net dot fully connected dot in features. Now I'm going to create the last few layers, that is the fully connected layer and the output layer. So I'll call it as net dot fc, the fully connected layer, and nn dot sequential. So usually we will use the sequential for building the network. Similarly, I'm going to use it here. Now create the networks. So that will be nn dot linear of num features, comma 256, and after that nn dot relu. So relu, yeah. So this is the activation layer, and after the activation layer I will have a dropout. So dropout It can be 0.3, so it won't overfit. And for the last layer, I will have one more fully connected layer. So nn dot linear of 256 comma num classes, and num classes. And for this one, I will have a activation function nn dot log softmax dimension equals 1. So this is our whole network architecture. So for one part of like feature extraction, I'm just using a pre-trained model, and in the last few layers we are just creating our own fully connected layers. You can also have like multiple layers if you want. I'm just going to have like two fully connected layer and one output layer, so that is enough for us. And finally, network equals net dot CUDA, that is if GPU is present, if device, else net. So if device is not none means it will specify the CUDA, or else it will just use the CPU version. And finally we will return the network. So that's it. Create last few layers. Okay, that's it for our model creation. This is use GPU if any. Okay, now that's done. Let's get the model. Now model equals get model. Okay, I didn't run this. Now, okay, now it's downloading all the pre-trained weights. See, it's like a bigger network. That's why it's have like 230 megabytes. So after loading, it won't download again. It will just reuse it. So it will, yeah, it will be completed. Okay, now we are facing some error. Okay, currently I didn't enable the GPU. That's why we are facing this error. So if you want to enable the GPU means just click on this button, and here you can see accelerator, set it as GPU, and turn on this GPU. So this will just restart the session. We can rerun it again, and I will resume from this step. So the session is taking longer to start. So in the meantime, we will just complete our remaining things. So we will create the criterion and the optimizer, that is the loss function. So criterion equals nn dot cross entropy loss. So this is our loss function, and after that we will have the optimizer torch dot optim dot sgd. You can also use Adam if you want. So model dot parameters and learning rate equals 1 dot. So initially I'm just setting a higher learning rate. Slowly it will reduce. Momentum equals 0.9. Maybe we can have 0.1 instead. Let's see. Okay, these are the criterion and the optimizer. And after this, we will just print the model to check the whole architecture. And this will, we can do it. So now we will find the total parameters and the trainable parameters. So find total parameters and trainable parameters. Okay, now the total params equals sum of p dot numal for p in model dot parameters. So this will calculate the total number of parameters and we can print it. So print format. If you use this format symbol means we can easily represent the parameters. Total underscore params colon comma, and here total, okay, this will be inside the quotation. So total parameters, so that's done. And after that we have to see how many trainable parameters are there. So trainable underscore params equals sum of p dot numal for p in model dot parameters if p dot requires grad. That is, what are the layers we have set it for training. If it is true means it will just calculate the total of that parameters alone. So this is the trainable parameters. So similarly we will just print it. So trainable params, this will be training parameters. So numal means is just like a number of elements. It will just return the total number of elements in that particular layer. So we are just iterating through the layers only. So this is done. I think I have to like see what is happening and restart everything. It's not running properly now. So I'll just finish everything and we will resume it from here. Okay guys, so I have like restarted the session again. So I'll just run this function and again we will be getting the model. So it's actually downloading the model, I guess. So after this we will set the criterion and optimizer, and finally we will print the model. So it is printing the whole architecture here. So you can see this is convolution layer 1 and here we are having multiple sections. So this is the whole architecture. So it's just a bigger one. And finally this is the one we are having sequential and fully connected layers at the last. So we will just uncomment this because this will occupy a lot of space. So I'll just comment this one. And after this we are having the total parameters here. So here you can see the total parameters is around 58 million. So this is like a huge number of parameters. If you set all the training parameters as like trainable means it will take a longer time. So currently we are just having the fully connected layers, that is like 525,000. So these are the training parameters we are having. So we are going to train the weights for this parameters alone, and later on we can unfreeze a few layers at a time and train your model. So after this we have to create a function for training. So here this is like a bigger step. So we'll be compiling everything into a single function. Steps for training and validation. So def train model. So here I'll be passing the parameters. First we will pass the model, Dataloaders. We have two Dataloaders, right? So here we have two Dataloaders. So we will create a Dataloaders dictionary that will contain both these Dataloaders. So we will call it as loaders equals train. So that will have a train loader, and second one is val that will have val loader. So it will be easier for us. Now here we'll be passing the data loaders, and after that we will pass criterion and optimizer number of epochs epochs equals, by default I will have 5, and I think that is enough. So now this should take like a longer time for us. So first we will calculate the starting time. So I will have start time equals time dot time, and after that we will create a list, that is val accuracy history. I will have a list. So I'll also comment this one, set starting time, and after this we will create a variable called best model weights equals copy dot deep copy of model dot state dix. So this is just model weights. I'm just copying the initial weights of the model. So later on we will be just updating this best model weights, and here best accuracy equals 0. So initially it will be 0. We will have this train model itself to have a common format for everything. Now after that we will start the loop. So for epoch in range of num epochs. So in this loop we are going to set all the functions. So first we will set the epoch, print epoch. I will have the format also. So epoch, here we will have the epoch and out of how many epochs, that will be num epochs. So this is done. I think this will be num epochs minus 1. So let's say the num epochs is 5 means, so starting epoch will be 0. So 0, 1, 2, 3, 4. Like that only it will go. So that's why I'm having minus 1 here. And after that we will have some special characters to like segment it. So hyphen multiplies, I will have it like 15 times. So we will adjust it later if we want. So here we will have training and validation space. So each epoch have training and validation phase. So for phase in a list, so here we will have train, and after that we will have validation. So after completes the training we will do the validation. So for training we have to follow some flow, and for validation we have to follow some flow. So I will explain all those things here. So first, if phase equals train, so if this is a training phase means we will set the model as training. So model dot train. So here set model to training mode, else model dot eval. So this is validation mode. Set model to evaluate mode. So these are the two modes we are having. Training means it will update the weights in the overall process, but in the evaluation we don't have to do any of those things. We will just try to predict the output in the eval states. So you have to set the state. So this is the first step, set mode for model. So the first step is done. Now we have to initialize few variables. So we have to calculate all the accuracy and loss by ourselves. So that is like some disadvantage of Pytorch, but we can do a lot of customization here. So running loss equals 0 and running corrects. So this is like accuracy, how many correct images we have predicted, like correct labels. So that is 0 and final output equals a list. Now here iterate over data. Now we are going to iterate using the data loaders. So for inputs comma labels in data loaders of the face. Okay, this is a variable. So if this is a train phase means we will be using a train loader. If this is in validation phase means we will use that validation loader. So that's how it works. Now inputs equals inputs dot to device. So currently we are having GPU, right? So I'm just transferring the inputs to the GPU. So if you don't have the GPU means we'll be transferring everything to CPU. And labels also we will do the same thing. Labels dot to device. Okay. So this is move data to corresponding hardware. Now after that reset or 0 the parameter gradients. So why we are resetting the parameter gradients is usually in the Pytorch it will calculate all the gradients while training. So for each epoch or after each update we have to reset the gradients to 0. So for that optimizer dot 0 grad. So this will set all the parameter gradients to 0. Now after that we will go for the actual training or validation process. Just have this. Okay, now with torch dot set grad enabled equals phase equals train. So only for training we will set the gradients as enabled. So we can calculate the losses and update the weights in the network. So inside here we will have outputs equals model of inputs. So we are just predicting from the inputs, and after that we will calculate the loss. Criterion of outputs comma labels. So this is the outputs we are predicted from the model, and this is the labels we are having. So we will calculate the loss here, and after doing that we are going to do argmax here to get the predictions. So this is like this will have the maximum values, and this is have the maximum index, that is the actual labels. That's why we need this variable alone. So here torch dot max. So this is like a argmax function. It will just give you the index of higher probability. So I will have outputs comma 1, and after this we are going to do the back propagation and update the weights. So if phase equals train, loss dot backward, it will calculate all the losses, and here in optimizer dot step. So this will update all the gradients, or this will update all the weights in the network. This is, I will simply say back propagation in the network. Okay, that's done. Now after this, the training phase is over. Now we will calculate the loss and the accuracy. So it will be running loss plus equals. So remember, this data loader have some batch size we have set, that is 32. So for each 32 samples, we are updating the loss, like finding the loss and do the back propagation, updating the weights. And here in the running loss, we'll be adding all the losses. So that will be loss dot item. So this will give us the mean of all the losses, multiplies inputs dot size of 0. So I'm just multiplying the mean into the size of the input, that is 32. So we will be having the total loss here. And after this, we'll be having running corrects plus equals torch dot sum of preds equals labels dot data. So this will just calculate the total number of corrects. So if prediction equals the actual label means, it will just increment the sum and we will be having the total corrects. So this is iteration over the data. After completing this, we will go outside the loop, and here we will calculate the overall epoch loss and accuracy. Calculate loss and accuracy for the epoch. Now here epoch loss equals running underscore loss divided by len of Dataloaders of, is that Dataloaders or, okay, this is Dataloaders, and this is also Dataloaders of face dot dataset. So this will give us the total length of the dataset, and I'm just dividing it by the loss. And now epoch accuracy equals running corrects dot double, I'm just converting into float, divided by len of, again this same thing, just okay. Now that's done. I don't know why the kaggle is like not at all working properly. So currently we are just calculating the loss and accuracy for the epoch. So this will do this for the training and the validation phase. Now after this, we will print the loss and accuracy for the training. Print loss and accuracy for training and also validation. So this will do both of these things. Validation, now print. Here we'll be having the format of what are the things we need. So first we will have the phase. So we will know what phase we are in. Phase space loss colon. We will have the loss, that is epoch loss, and we will be having the accuracy equals epoch accuracy. That's done. And here we will just copy the best epoch. So here we will just copy the best weights. So update the best weights. So here if phase equals val and epoch accuracy is greater than best accuracy, then we will have best accuracy equals epoch accuracy and best model weights equals copy dot deep copy of model dot state dict as we have done before, or else we will have validation accuracy. Okay, this is not a else. If phase equals val, then we will have validation accuracy history dot append val. Okay, this is just epoch accuracy. Okay, that's done. Okay, this is just the whole epoch. As you can see, this is like a bigger one. See, this whole step is like a single epoch. You have to do all these things here in Pytorch. Sometimes I prefer like TensorFlow because of this like huge amount of code. So after this, we will have, okay, this is inside the epoch. So I'll just have a print. It's very difficult to find the indentation. And in the outside, I will calculate the end time, and time equals time dot time minus start time. Now I will have print training completes in a format. So here I can specify the format colon dot 0 f minutes, and similarly for the seconds dot 0 f seconds dot format of. So you can use both kind of formats for printing. So this is one type of formatting and this is other one. This is like a format specifiers, and here we will pass the variables for these two brackets. So that will be end time divided by 60 comma end time modulus 60. So this will give us the number of minutes and this will give us the remaining seconds. So that's it. I'll just have some spaces for neatness of code. So after printing the time, how much it takes, we will print best val accuracy so here colon dot 4f, that means 4 decimal points I can allow, dot format of best accuracy. Now we can load the best model weights to the model, because each epoch have different validation accuracy. It will like train the weights differently. So we will just store the best model weights and load it at the end. So load best model weights equals model dot load state dict. I don't know whether it's adjust or not. Load state dict best model weights. Okay, after doing this, we will just return the model, return model and the val accuracy history. So this is the whole function for training, guys. In TensorFlow, it's like a single keyword. You will be just passing the model, passing the data loaders, and setting the criterion or loss with optimizer, and just setting the epoch. But here everything will be customized. Like every process we are just doing it by ourselves. If we do any mistakes, means it can also be easily debugged. So that is the advantage. So I guess this is the whole process. It's just a lengthy one, but yeah, run this. Okay, I guess I have to rerun it all. So this will just rerun all the things once again. Now we have rerun everything. Let's train the model. So train the model comma accuracy, that is the result we are getting, that is returning from the function, equals train model of model comma Dataloaders, model comma model equals Dataloaders equals loaders, criterion equals criterion, optimizer equals optimizer, and after that number of epochs I will set it as 5, but it will take a longer time definitely, and I guess that's it. Let's run this. Okay, as usual we are getting some errors. RESTnet have no attribute state dict. Okay, so this is state dict without yes, and here we have set it right. Okay, run this. Okay, now the first epoch started. Let's wait for a while to check how is the training and validation accuracy is coming up, and after that we will check more of these things. Now the training is actually started. Here you can see the GPU utilization and how much memory it is occupying. If you have higher memory means you can definitely like unfreeze some of the layers and train it. If you unfreeze all the layers means it may throw some errors because of not sufficient memory, and the CPU is also utilizing because it have to load the data, so that processing power will be needed. I think we just have to wait for a while until the model until the training completes, and after that we will unfreeze, and after that I will show you how to unfreeze some of the layers and train it for those layers alone. So the first epoch is already completed. We are getting around 61% training accuracy, but the format is not at all better. I think we have to reformat here. I'll just stop this once because I definitely have to reformat the print statement here. The face, yes. So here I'll just format it like this. Remove everything. So here I will have the face and loss space again colon dot 4 digits we need, and accuracy similarly colon dot 4f, and after that we will have dot format of face, and next the epoch loss and epoch accuracy. So that's done, and I'll also change the configurations a little. So this is the configuration. I am having the train batch size as 32. I'm just changing into 128 to just complete the training process quickly. 128. Okay, let's run this and rerun the training again. So this will do the training for a while. In the meantime, we will cover the remaining steps. So after training the model, if you want to save the model and model weights. So torch.save of model comma, here you have to specify the path with the file name. So currently I am in kaggle, so I have to specify kaggle working / best model dot h5. So this is for saving the model. To save the weights, again torch.save model dot. So here this is state dict, and I will save it the same directory. Instead of this h5, I will just call it as best model weights. Okay, using this you can save the models and the model weights and reload it later. And after this, if you want to unfreeze or freeze some of the layers, like all the layers, freeze or unfreeze all the layers. So I will have freeze as a variable, boolean variable. I'll say true. Change the variable name as unfreeze equals true. So to do that, for param in model dot parameters param dot requires grad equals unfreeze. So if this is true, means it will just change all the layers as trainable. So you can retrain it again with all the parameters, but it will increase the training time, because as you already seen, we have like so many parameters. So 58 million parameters. So that is like a huge size. If you want to freeze all the layers, means you just have to set it as false. To freeze, set it as false. So this is the code snippet for that. What happens if you want to unfreeze only specific layers? So for that, I will have a separate code. Unfreeze selected layers. So this will be layers equals, let's say I want to unfreeze the first 4 layers, list of range of 4. If you want to unfreeze after like intermediate, after 4 to 7, means you just have to specify 4 to 7. So it will just create the numbers only. So if you go for layers, means it will just have the list of numbers, that is 0 to 3. Now we will iterate the layers, and here I will have index, that is 0, for layer in model dot children, and if I in layers, we will do the same kind of approach for param in here layer dot parameters. So this will be param dot requires grad equals true. After doing for this layer, I'll just increment I by 1. So this will just unfreeze the selected layers. Using this list, you can customize the range, like start and ending range. So let's say if you want to freeze all the layers, you'll just say false, run this function. And if you want to unfreeze the first 4 layers, means you just run this function. It will just set the parameters as true, that is trainable, and you can rerun this train model again to just train that particular layers alone. That will be very helpful for fine-tuning the model. So currently we are having training accuracy around 61% and the validation accuracy around 62%. So that is a decent one. Currently we are just training only the fully connected layers. So we will see, it will take some time. So this is how we can freeze and unfreeze the layers, and apart from that you also have few techniques, but yeah, for the beginners this is enough. I think this is like more than enough. In the next step we will see how to do test prediction or test the model. Testing the model. So before testing we will just clear all the cache in the CUDA device. So torch.cuda.empty cache. So this will just empty the cache from CUDA device. Currently we don't have to run this. After the training we can run this command to free some memory. And now we have to define another function for test prediction. So here I will define the function. Before that I'll just have the steps. So I will have the steps for model prediction. Okay, this is prediction. Now we have to set the device again. So device equals torch dot device dot, sorry, this will be CUDA. If you don't have a GPU means set it as CPU. If you don't have GPU, set it as CPU. Okay. And after that we will just move the model to the device, model dot to the device, and after that we will get the prediction. So pred equals predict of, so this is the function we are going to create. I will pass the model. For this example I will just pass the validation loader, so that is enough. If you do have a test data separately means you can create a data loader for test data set and pass that data loader here, and apart from that I will pass the device. So this will get the prediction for all the validation inputs, and after that we have to get the labels alone. So for that prediction equals pred dot argmax of access equals 1. So this will get our labels. So this is the step for the model prediction. Now here we will define the function for predict. Def predict, will pass the model, data loader, comma device. Okay, now for the evaluation or the prediction purpose, I already told you, we already covered those steps here. So this is how the evaluation done. We are going to follow the same procedure. So set the mode, set mode to eval. So model dot eval, and after that we will initialize a variable called fin output equals list. So this is our final output we will return. Now with torch dot no grad, we are not going to trade, that's why I'm just having it as no grad. For images comma targets, this is just dummy targets in data loader. So this will just return the images and targets, and we will just move the images to the device. So image equals images dot to device, and here target equals target dot to device, and after that outputs equals model of images. So this is the test images. This is how we are going to like predict the outputs, and after we got the output, finout dot append f dot softmax. So this is the function we have imported. F is the alias name. Softmax outputs comma dimension equals 1 dot detach dot cpu dot numpy. All these are functions. I am just doing this process and detaching from the memory and going into the CPU, and in the end we will get the numpy array as the result. So after doing this, we will return np dot concatenate of finout, because we are appending for each batch. That's why I am just doing the concatenate to concatenate all the outputs, and finally we will be getting the prediction. So now we have to wait for a while until the training completes. I guess it's stuck at some point because of that SGD. I guess I have to like set it for Adam. So I'll just stop this. Currently we are getting validation accuracy as 62%, and here I can change the optimizer to Adam and retrain it again with some learning rate. So I'll just comment this one, and here instead of this I can have Adam. Model dot parameters will be same, and I have to set the learning rate. You can have 0.001. Run this, and after that we can retrain it again. But we are getting around 62%. This is just an example. I'm not going to like fully go for it because this will take a long time. I will just show you how to save and all. So if you run this, it will just save the model and weights. If you go into kaggle working, so here you can see the best model weights and the model. You can reload it if you want later. And here I am gonna show you how to unfreeze and freeze all the layers. Let's say I am going to like freeze all the layers. Freeze it. And I'm going to unfreeze the selected layers here. Unfreeze it. And I'll also show you how many parameters are trainable now using this. So before that we are having like less currently. So the total parameters are around 58 million. Now we are having around 9,000. Let's say if you unfreeze all the layers, unfreeze and run this. Now the total training parameters are like 58 million. So if you pass it, means it will definitely throw some memory errors, because this is like the whole model will be placed in, all the parameters will be in the GPU. That is definitely out of memory. Let's again freeze all the layers. So using this snippet you can clearly see it's having 0 to 9, that is the range, and the total number of bigger layers is 10, and under that we have like various parameters. And here I'm going to unfreeze the first 4 layers. After unfreezing, I will run. Currently it's just showing only 9000 trainable parameters. Let's increase the range to 7. So now you can see there are like so many trainable parameters are there. It's around 43 million. So play around with this thing. So I think this depends on you. If you unfreeze specific layers, means after unfreezing you just retrain the model again to fine tune those layers. So this is just like an advanced technique for you. I guess even for 5 it's having a lot, I guess. So currently I'm just okay, I just have to freeze. Okay, if you just unfreeze the first 5, I'm having like 225 training parameters. So that is good for us. Gives the number of layers. Okay, so that's done. You can do the training as it is. Now we will empty the cache here, and after that, okay, this is predict. Run this function. Now run this one. This will again take some time to do the prediction for our validation data. Okay, I just made a mistake here. This is targets. Okay, run this. I guess the prediction is done. Let's display the top 5 predictions. Pred 5. And we also display the X test and the actual labels. I think we already have. That is y test dot values of 5. See, so currently our model like predicting every output as 3. That is the class label for the higher distribution. That is this one. It's having a higher distribution. That's why everything is predicted as 3. And here even in the y test values, we are like having 3 out of 5 values are correct. This is how you can do the prediction. And I'll just rerun the model just in case. So it will just running. In the meantime, I'll just show you the actual notebook. I have used it for the contest. Okay, so this is my actual notebook. I have done like so many things. This is importing models, and this is like plotting the images function, and we have done all these steps. But this is like feature extraction and do some clustering. So I'll just left it out. So this is some kind of like inference or exploratory I have done, and this is the configuration we have gone through. And this is like additionally I have like center crop, random crop, and this is the Cassava dataset, and this is the sampler. I have told you before, I'm just using a weighted and a random sampler to have like equal distribution for the class variables, and using that I'm just getting the sampler. And I also pass the sampler here in the data loader. I can pass it and comment it here. And these steps we already covered. So for this model, I just used ResNet 50. So, and this is cyclical LR scheduler. This is like a custom function. I just added a few more things for better model. And this is the whole model architecture. We'll just skip through. And this is the whole training model we have seen. And this is the training accuracy I have got. It gone around 93% accuracy. And in the validation state, when I predicted it, it gone up to 87%. So that is a decent accuracy for us for just like a baseline code. And I have like freezed all the layers and unfreezed selective layers and train it again. So that's how I have achieved these results, because fine tuning is really important. And after that I just do the saving part and do the prediction for the test data here. And finally I have submitted the results. So that's how the whole process works. So I have a separate notebook for submission, because that's how this contest worked. And this is just a sample submission, and everything remains the same as usual. So let's switch back to our actual notebook. So I think that's it, guys. We have covered pretty much everything except the actual training part. It will take a longer time, definitely. I already have my own model like trained and loaded. I can also like load that model and show it for you guys. So for further steps, what you can do is you can get this code from the GitHub and do this unfreezing and freezing the layers and retrain the model. Or you can also use some kind of different model or use your own model, so that your wish. And after that you can do the testing and see how it works. But this is the overall process for the complete Pytorch. So we have done the training, testing, we have done pretty much everything except that advanced techniques. So if you like this video and if you want more like this means, please leave a comment below so I can work on those projects. Apart from that, if you like this video, hit the like button and don't forget to subscribe the channel for more videos like this. I'll see you guys in the next video.